Now let's look at the topic of design patterns. What exactly are design patterns? To put it in a nutshell, design patterns essentially are a form of distilled experience. What do I mean by that? Over the years, a number of highly skilled and intelligent engineers and developers have worked at various different kinds of software, and based on experience they have come up with a number of different observations, right? These are sometimes called best practices or coding style conventions, naming conventions, and so on, right? And all of these are essentially guidelines that tell a new or even an experienced developer that if you follow these practices, a number of good things happen. One of them could be that yes, there is a lesser chance of bugs in your code. Another could be that it makes it easier for someone else to understand what your code is doing and thereby build on top of it, right? Now, the same thing is taken to a certain level when we discuss the topic of a system level architecture, right? And patterns have been observed over there in terms of how you could go about trying to solve certain kinds of problems, right? And that essentially is encapsulated in the idea of a design pattern. In other words, you are trying to design a solution to a particular problem, and these kind of patterns have been found to be common solutions to such problems in the past, and therefore it is recommended that you at least understand what such patterns are and then see whether one of them can be used in order to solve your problem. So what we are going to do now is to take a look at a few such examples and sort of see how it makes a difference to how you go about designing software. One of the first and foremost patterns corresponds to the concept of something called a state machine, right? Now, from the course on digital systems, you have already heard of the idea of a finite state machine, right? Essentially what it says is there is some kind of set of registers which hold certain values, and what the finite state machine does is it looks at the present state of those registers, it looks at the inputs that you have, performs some computation, usually using combinational logic, and then updates the state, while at the same time also generating certain outputs. Now, that's purely at the circuit level, right? Digital logic. But the example of home automation that we looked at a while ago follows exactly the same principle. There is a certain state associated with the system, right? And that state essentially corresponds to some numbers, some memory of the system. In this case, it could be something as simple as what's the current temperature, what's the current value of humidity, and maybe a few other parameters that are relevant to the system being designed, right? So, in other words, there is some notion of something called a system state, which is a memory of what the system is currently doing, right? And the way that we think about the program that we are trying to develop is that we have a current state and we want that state to evolve with time. We want it to basically develop based on other inputs that are coming in, possibly through the sensors or ultimately through sensors in any kind of embedded system, right? And we want to perform a certain computation that then tells us what should be the new state of the system, right? Should I sort of detect that the temperature has risen too high and maybe the house is on fire, or should I find that things are getting too cold and maybe the water pipes are going to freeze, right? All of those are different options that the system should be capable of handling. So the evolution of the state of the system and how to respond to it is a sort of natural pattern or a way of thinking about what an embedded system is supposed to do. And of course, the idea is that you should be able to compute certain outputs depending on the present state as well as the inputs that you see currently. Now, an example of this, some of you may have actually come across, possibly watches or small alarm clocks where you pretty much just have one or maybe two buttons, right? And you have to do all the control using those two buttons. Now, how do you set the time, right? The hour, the minute, the date, and also the alarm time, turn on the alarm, turn off the alarm, all using two buttons, right? It's not an easy thing to do. So the way that those alarm clocks work is by using the concept of state, right? So you could for example, have something, if you just had an LED with a single button control, you could, for example, say that, if I press the button once, turn the LED on. If I press it one more time, start blinking, right? You have probably come across something similar, and in fact, the alarm clocks use something of that sort. You just press it once, it goes into one state where it shows you maybe the date. But if you press it twice quickly, usually within a short amount of time, it allows you to go into a state where you are allowed to change the time, right? And in each of those cases, after a certain timeout, or maybe after it has blinked for a certain amount of time, it might just decide, okay, now stop blinking, the person has gone away, they are not really interested in changing the time, let's get back to the original state, right? So it's easy for us to describe a system that works like this, right? Now, how would you go about designing it in the first place? If I told you that you need to design an alarm clock, but you have only 2 buttons, or maybe even only 1 button with which to do it, the first thing is you need to sit over there and say, okay, what are all the different operations I need to perform? And then figure out, is there a way by which I could actually systematically get through each of those different modes of operation, right? And one way by which this is done is to use something called a state diagram, right? And this kind of a structure is the common way of understanding how finite state machines work, right? You can see why it's called a finite state machine over here. These sort of rectangles that we see over here are essentially the states of the system. So you can assume that it starts off in the off state, right? This means basically the LED is off, right? As marked over here, that's essentially the initial state of the system. Now, these dashed lines that you see over here, by the way, are indicating they are just comments, right? So they don't really indicate, they are not part of the state diagram as such, they are more there to understand what the diagram does. Alright, so let's assume that the system has been switched on, and when it gets switched on, it basically moves into the off state. What does that mean? That the LED is off. Now, I have only 1 button. What can I do with it? I can press it. And what this tells me is, okay, now go into a new state, and in this on state, I'm just going to turn the LED continuously on. Okay. Now, you could have just decided that, okay, the button press just acts like a switch, but that's not exactly what we are saying. The button is pressed and then released, right? So it's not like I can just take the button and connect it up to the LED. I actually need to have some logic which says, hey, the button was pressed once, and once I know that the button was pressed once, I move into this new state where I'm going to leave the LED on. But now what I'm saying is, if I press the button one more time, I'm going to go into a new state which I'll call the blinking state, right? So these names, the off state, on state, blinking state, the names of the states don't matter, right? You can choose something that makes sense to you and to whoever else is developing the system along with you, or who needs to understand how the system works. But as far as the computer, the program is concerned, all of these just get encoded as some kind of numbers, some codes corresponding to the different states. The state transitions that we have are, from the off state, press the button once, you go into the on state, press the button one more time, you go into the blinking state, right? Now what happens in the blinking state? 2 options. Let's say I press the button once more while I'm in the blinking state, I'll just go back to the off state. Or it could basically have some kind of a timer, right, which basically every time that the timer expires, maybe after 1 second or so, it makes the LED blink, but then it also increases blink count, which is some variable that you have inside the system, part of your system state, right, but not one of the states that you have in your state machine. It's part of the memory of the system. Once the blink count has exceeded a certain number, I automatically go back to the initial or off state. Okay. So what would the behavior of such a system be? I switch on the system, LED is off, I press the button once, it goes into the on state, now the LED is just solid on. I press the button once more, it goes into the blinking state, and it blinks at some frequency determined by this timer tick. Now let's say I just leave the system as it is, it blinks 5 times, goes back. But in the meantime, if I didn't wait for 5 seconds but immediately press the button again, it also goes back. And now it waits once again. It's not going to do anything in the off state, it's just the LED is off and it just waits there for me until I press a button, in which case I go back to the on state. This is a finite state machine, and as you can see, it can be used in order to solve this problem of creating a state based response for a system. So there are a few concepts here that are worth sort of emphasizing. The states essentially represent the different modes or conditions that the system can be in. Events are triggers that can cause state transitions, right? In the previous case, the button press was the event. The transition by itself defines how the state moves from one state to another. So for example, when we had a transition from off to on based on one button press, it basically says that the initial state is off, the final state is on. What is the condition for the transition? Button should be pressed once. Okay. And actions. What are the actions? When you are in the off state, turn off the LED. When you are in the on state, turn on the LED. Right? Those are actions which are seen by the outside world. They do not correspond by themselves to part of the state of the system. They are actually things that are observed outside. So these are sort of the primary concepts that apply not just to a digital system or a digital logic based system that you might be designing for implementing a finite state machine, maybe a traffic light controller. It works perfectly well in the context of embedded systems design. Not just that, it actually applies even in the context of operating systems, graphical interfaces, and various other things, especially when there is some kind of interaction involved. The whole notion of events and states and how they can be used in order to generate complex behaviors is what we are making use of over here. What are the benefits of a state based approach? Predictability. You have a very clearly defined system behavior for each state, and if you want to modify or extend that system behavior, once again it's quite easy to understand what the different states are doing. You could add new states in order to bring new kinds of functionality, right? And in general, understanding and sort of modifying such systems is relatively tractable. It is not easy perhaps, but it's at least doable in most cases. It can also simplify debugging because tracking the system behavior, as long as you know the system state, if you have some way of monitoring the state of the system, right, it becomes relatively much easier to identify where issues in the system are coming from. And it is also a very efficient way to implement things, right? From digital systems, you already know that states can be represented using just log n number of flip-flops, right? If you have n different states, you can basically represent them using log n flip-flops. Now, in an embedded system, you probably don't care to minimize it that much, but what it means is that even with, let's say, just an 8-bit number to represent a state, you could have potentially up to 256 different states, right? And usually you don't want to go for such large designs or large state machines for other reasons. But what that means is that the state definition and keeping track of it is by itself not going to require a huge amount of resources. So how does this get translated into actual code, right? A very common way, the typical way of representing this would be something like this. You use some kind of type defs. Make use of what the language provides for you, right? C provides the notion of enums, enumerated data types, or type defs, right, which can be defined as type defs. And what you can do is you can basically say, okay, you have a few different states: state off, state on, state blinking. And of course, we know behind the scenes what ends up happening is that the C compiler would actually create, let's say, an 8-bit value, right, with the appropriate values 0, 1, 2, and so on, right? But just keeping in mind that the whole point of the language is abstraction, you should not rely on the fact that, for example, state off corresponds to the value 0 or state blinking corresponds to the value 2. Why? Because at some point I might decide to introduce a new state somewhere in here, and the value of state blinking might become something other than 2, right? As long as I use these enumerated data types, I don't care. It means that my code is easy to understand and can be modified without having to make any other changes somewhere else. Where this can sometimes become a problem is if we don't have a way of actually representing the state while debugging. This can become a problem because this value will basically be shown as 0, 1, or 2, and I need to then identify what does 0, 1, or 2 correspond to. But what you can see is there are states defined as enumerated data types, and there are events which are again defined as an enumerated data type, again mainly for convenience, right. You can also have another control structure corresponding to an LED, which if you look at it basically has two things. It has something corresponding to the current state, and it also keeps track of the count. So this LED control is actually a more complex form of state that is being maintained for the system. At the end of the day, it is still part of the state of the system, but it also contains things like a counter which can decide when I need to get out and go back into the off state. Okay, so that's as far as the definitions are concerned. How does the transitions or how does the code itself look? Once again, this is relatively easy to write, right. What you have is that you have some kind of a handle event function which basically uses some kind of a switch case kind of structure, which literally looks at which case your current state is, right. LED dash current state, right. If it's in state off, check for the event that has happened. If the event was a button press, change the LED current state to on, printf LED turned on, right. In other words, if I go through this switch statement and I'm currently in the off state and I find that the event button has been pressed, my state will change to state on, which means that the next time I come in here as part of my loop, I'll see that the LED current state is not case state off, it is state on instead, right. Where I can see that, if I'm in, once again, if a button is pressed, go into the blinking state and initialize the blink count to 0, ready to sort of count up to 5 and then get out after that. Okay. So as you can see, the states that we drew in the state diagram literally translate very easily into cases in a switch case statement. So even writing this code and compiling it can result in very efficient implementations. This is not the only possible coding style. Switch case is the most common. However, it can become sort of unwieldy for complex state machines. Now, this is something you have to be careful about. Yes, switch case statements can become problematic for complex state machines, but if you have complex state machines, you probably should also rethink why you have complex state machines in the first place, because even though we said that debugging is made easier by the fact that you have states, the interactions between states can get to the point where understanding why something ended up in a particular state can become very difficult. Now, having said that, if you do have systems with large numbers of states, you can probably define those states into a state table and have some kind of a transition relationship defined in the state table, right? Basically becomes a lookup in some sense. It becomes easier to maintain large state machines by doing this. And of course, if you have access to a language like C++ with classes and object orientation, right, there could be a way by which you could actually define each state by a different class, and the transitions could then be sort of just method functions corresponding to the different classes. It makes your overall system a little cleaner to represent, right? So once again, the object here is not to get into the details of coding styles. We gave one particular example, but there are different ways by which you can implement these state machine based systems. Now, are there challenges? Yes, of course, right? It doesn't come for free. State machines can become very complex. The more the states and transitions that you have, even just understanding what is going on, let alone drawing it. I mean, even drawing it can be difficult, let alone fully understanding what is happening in there, right? The other thing which the previous example didn't really need to concern itself about is that very often you are also concerned about timing, right? And in real-time systems, you might be interested in the exact time at which a particular event happened, and based on the relative time between different events, the transitions have to be different, right? Ensuring proper timing for state transitions can be difficult. You can get into so-called deadlocked states, right? Things where you get into the state and you don't have any way of getting out of it, right? Such things can happen. There is some amount of theory that also talks about under what conditions it can happen and how to avoid such things. But in general, the only way to do it is try and keep your system relatively simple. And finally, although we haven't talked too much about software testing, testing becomes very hard when you have states, because unless you know in which state your system is, you cannot really try to test its behavior under different input conditions. More than that, getting a system into a known state from some other state itself could be a hard problem. There is not always a guaranteed set of transitions that will get you into a given system state. All that basically combines to make the testing of such systems quite difficult in practice. Okay, so state machines were one particular design pattern which is commonly used in order to sort of structure how certain problems can be solved, right? But there are other patterns. What I'm going to do over here is just look at a few of them at a very high level, right? One good example is something called the observer pattern. It basically indicates so-called one-to-many dependencies. And as an example, consider that you have a motion sensor somewhere in your house. The motion sensor is triggered, maybe something has gone in front of the sensor and indicated that there was movement. Now, the movement could be one of many different things. It could be an intruder trying to break into the house, in which case the alarm system needs to be triggered. It could be that your pet cat has come in and you need to sort of have some kind of feeding mechanism automated so that the cat can be given food. It could be a garage opener basically saying that your vehicle has come close to the house and therefore maybe open the house. Now the point is, all of these are different possible responses to the motion sensor. Which one should actually get triggered? Well, one way of possibly doing this could be that you actually have different functions looking into each of these, and all of them get notified the moment the motion sensor gets activated. Not all of them may respond, but it's possible to write your code in such a way that each one of them then basically goes, does its own thing, figures out if it's the one that needs to respond, and if necessary takes over and then starts doing the work. Of course, there's a problem if both the cat feeding sensor and the garage door opener, or rather the alarm sensor and the garage door opener, think that it's their duty to respond to this particular operation. You might end up opening the garage door even though it was an intruder who was coming in, right? So designing such systems, you have to be careful, but the point over here is not about that. It's about how a single action could trigger multiple different computations that need to be performed. In this case, all of these different things that need to be notified are called observers, and this whole approach that we are using is something called the observer pattern. Now, how do we do observers in practice? There is a notion of something called callback functions, right? And in the context of C, that is usually done using what are called function pointers, right? So a function pointer basically allows you to actually have a pointer that could point to one of many different functions, and possibly what you could do is each time you want to register one of those functions as a possible somebody that needs to respond to a particular event, you have the ability to basically add this callback function, right, which is basically an observer callback as defined over here. You can add this into the code that you have already written, right? Now what that means is that the notification part that I talked about, right, could just be that if the event actually happened, I simply need to go through all the list of observers that have been registered so far for this event and call those particular functions. Observers of event is a function call now, right? It was a pointer to a function which basically gets called. I could, by registering multiple callbacks, have multiple different things that are registered to respond to a particular event. And this is a common enough practice that it actually makes sense to sort of abstract it out as a pattern and say that, look, if you do have something where there could be potentially multiple different systems that need to respond to an event, register them as observers. So this whole idea of using notifications in order to trigger the behavior of different observers is a key part of how the observer pattern works. Now, examples of the observer pattern could be things like, for example, when you have a sensor, right, and you both want to log the data into maybe a file, and to display it on a screen, right? And one way of doing it could be to have two separate functions, one of whose job is to actually log the data and the other one is to display it. It might be that due to various reasons, maybe your file system is full or your network is not working properly, the logging might not work, right? But you still want the display to be there for the person who is actually using the system. And by separating this out into two different observers, it can actually make it possible to do something like that. You could have a button press that can trigger multiple changes in different parts of a system, or something that you are probably actually quite familiar with in the context of either a laptop or a phone. You might have some trigger events which say that you have now come within range of Wi-Fi network that is known. So maybe the system basically comes into, it allows you, okay, now you are on Wi-Fi, you can start downloading the large downloads that you had paused while you were on the mobile data, right? You could move some apps into the foreground so that they can basically update themselves. You can check for OS updates. All of that can happen the moment that Wi-Fi gets activated, right? Once again, the same idea, right? There was a state change which in turn triggered a number of different observers and caused them to respond. Yet another pattern is something called a singleton pattern. This is commonly used, for example, when you have some kind of globally unique resources. A good example of that would be something like the communication primitive, the UART, right? Typically in a system you have only a single UART. What that means is, rather than sort of passing it around all over the place, you define it in a single place, and then you have certain functions which basically give you the get instance. It gives you access to the particular UART instance, and this can then be used in all the different parts of your code and will always be guaranteed to give you access to the single UART that exists in your system. It's sort of a form of a static or a global variable, right? But is trying to sort of encapsulate that within cleanly defined functions so that you are not sort of just directly going and modifying some kind of a global variable data. There are many other design patterns which you may come across at some point as you go through the development process. For example, it's a very common thing while developing embedded systems that you want to be able to send commands to them, right? You are creating a new system, you want to be able to send it a command. It could be as simple as turn on a light or make it blink or change the color, right? You create commands and you use that as a pattern which can be used in order to abstract away the way that you are actually updating the system. There are things called factory methods which are common for instantiating different types of objects, right? So you could have an LED bulb or an incandescent bulb or some other kind of light source, right? And all of them could be treated as different variants of the abstract idea of light source, right? Basically what it does is it allows you to create powerful abstractions. You can encapsulate all the information corresponding to light sources in one place and use so-called factory methods to actually decide whether it's an LED or a different kind of bulb, right? Once again, those of you who are familiar with object-oriented programming would realize that there are like very strong connections with the notions of object orientation over here. If you are not familiar with object-oriented programming, you don't need to worry about it, right? All that matters over here is this, that you understand why we are trying to do something like this. There is abstraction. You don't want to think about a specific brand of LED. You want to think in terms of a light source and then have some other thing which can basically decide later for you which form of light source or which form of LED is actually going to be used. Another common thing that you might come across as you build systems would be that you need to choose among multiple possible strategies, right? Let's say that you are trying to sort of do a remote controlled car and you basically need to decide how the motors are turned, right? You could have a simple linear control where essentially there's a number that's sent out to the PWM system and just decides at what speed the motor works. You could have a PID or a proportional integral derivative kind of control, right, which is a very common form of control used in embedded systems, which again we have not got into in this course because it sort of belongs more in the domain of control theory, but it's something as an example that we can look at, right? Or you might even have something much more complicated, maybe a neural network based controlling system to decide how a particular motor should be activated in order to reach a final target. Now, This could be very easy to implement, this might require a lot of computation. So which one you choose at runtime could actually be decided based on certain things like, are you running on battery, are you running on mains power, how much battery is remaining, right? How much time do you have in order to respond? So having the ability to choose between different strategies at runtime is again a pattern, right? There are many more such patterns. If you want to take a cynical view of things, you could probably say, hey, all of this is common sense, but as they say, there's nothing common about common sense. The point is to sort of understand why these things have been found to be useful and where they could be applied, without sort of getting too hung up on the fact that, is this particular kind of pattern, or should I be using this particular technique? Because these are more meant as guidelines to help you understand and guide the way that you think about system level design. But if you get too hung up on the notion of, is this a factory method, is this how this particular method should be implemented, is this pattern being done correctly, it can potentially cause that negative impact, right? In the sense that you are more concerned about how the particular thing is implemented than whether it's doing the right thing at all in the first place. So keep that in mind when working with these kind of patterns. Very often answers to the questions, is this the right pattern to use, may not be unique or perfect, and you need to be able to adapt as required.